Thank you, Magda. And indeed, this is one of the many contributions that Jörg gave to the ESO Science Archive, and so this goes out to him. And it's a demo of a few capabilities that the archive has, and it's not exhaustive, but it's meant to trigger your curiosity to go to archive.eso.org and explore the data that it's there. And I'm going to show a couple of capabilities again, and the rest is there. And we're always eager to help and answer questions that you might have as users. I mean, not necessarily here and now. So there's, as you've heard from Magda earlier, the archive contains, the ESO archive contains raw data and calibrations that go with them, and I'll show you how to reach there. Then process data, and of course here we have prominent data providers for this process data, and I'll show you how to get to those as well. Then there's catalogs, as you've learned, already knew before these days, and then of course there is programmatic access, and we already talked about a little bit virtual observatory, which is the foundation at the end of the day of all of this, as Magda has already pointed out. So raw data, science raw data in itself is very good, but pointless if you cannot calibrate it. And so the basic thing that the Science Archive does for raw data is to do this in an automatic way, and I'll show you how to do that. And automatic means that it's tuned to the calibration plans that ESO has set for each data type. Okay, so if you're doing that is automatic, and it should cover the proverbial 99.9% of the cases. If you have other needs on top of that, there are other ways of doing it, which are less straightforward by nature, by construction. So they're not shown here, but it's also possible. So this is archive.eso.org, and hopefully now the movie will start. Yes. And this is the home page. If you click on raw data there, you're taken to the raw data interface, and you can see that basically querying for raw data is limited, again by nature, to very simple characteristics of the data. And this is because raw data don't have a lot in common among each other. So there's not a lot of common base on which you can build services. So you select, say, instrument, a night perhaps, a program perhaps, a science, and you then go to your data, and here, before downloading, you're asked if you want to associate calibrations to your data, which generally speaking is a good move because, again, raw data by itself is not very useful. There are two flavors of calibrations in the ESO archive. There are the ones that are raw, so directly if you want to start from the pristine pixels at every level, or you can have data calibrations pre-processed by us, so that shortens then your what you need to do. You can also download night logs to see what the night was like when the data was taken. It has very important information. And also, as Magda has hinted at, if you start from raw data, you're also told, okay, look, there is also already reduced data for the raw data that you have selected. This is this last section at the bottom. Once you have clicked all the different types of data you might want to associate to your data that resulted from the query, then you can download them. There are a couple of ways of doing so. This is probably the most efficient one, which is a script that it's downloaded to your laptop, computer, and then you run it, and it goes and it just downloads all of the data to your disk. Very plain and simple. Data comes compressed in a couple of flavors depending on their nature, so you need to compress them, and then you're off, ready to go to feed it to some data processing tools. And then you can see here things are coming, and you can see that perhaps in this window here there are two flavors of data. The ones that come with M dot are master calibrations, so that's already pre-reduced in terms of calibration, and then the rest is raw data pristine. And then you wait a while and you're done. Okay, so that was it for the raw data. Then there is the process data, and this is where, in terms of archive, things become more interesting, because it's clear that it may be necessary in several cases for users, for you as a scientist, to go back directly to the raw data and do the most of every pixel. There may be cases like that, but in a lot of cases, you don't actually want to do that. You want to skip that step and go directly to the process data and do directly your science, your extraction, without bothering too much to reprocess the data. And there are a huge number of cases in which this is what you want to do. The other thing for which process data is more interesting than raw data is that it's much easier to describe process data in terms of the physical quantities of the data. So not exposure time, but say signal to noise or limiting magnitude of an image. Not GRISM name, which is often engineering and obscure to us astronomers, but wavelength coverage, or say not some generic seeing on the mountain, but the actual image quality on your particular frame, and so on and so forth. So this is when it becomes more interesting to explore the data from an astronomer's point of view, but it also becomes more challenging, since you have more information to share, to present this information in a way that's manageable, okay? And the way we thought of doing this was to present facets, which you see, there will be the movie also here, but just to show you this bottom right panel, these are facets, so these are important aspects of the data, again, image quality, wavelength coverage, etc., signal to noise, depth, etc. And this is the way in which you query the data. Each of those boxes, you click, you select, you put in a query directly, and you see all of the other aspects changing in real time to comply with your constraints. And this, we hope and believe, it provides a good way to explore the data. And we have of the order of 4 million files to navigate through. And then there's also a visual aspect, and I'll get to that in a few examples of seeing the results on Sky with the footprints, with previews, and other ways that make you confident that the data, that you found the data that you want to do then your science on without downloading everything. And then judging afterwards. So this is the homepage of the product archive of ESO, and you also get to hear from the archive.org from the homepage. So if you click, then you can enter a target. This is an example of a query. You start for a target, you do that, and you see 253, why not? And you see everything changing. The Sky zooms at the position that you are querying. So you have entered the constraint on the data is filtered on, and then you see, okay, this is some backdrop that you can change, whatever it is. This is DSS, but you have a choice of half a dozen backdrops, and you can see where the ESO data belongs then to on the Sky. And you have the footprints and this top, and then you have a tabular representation at the bottom that shows you the characteristics of whatever it is that you're doing. And what was happening here is that images were selected on and off as restricting the query only to those. But of course, you can do it for any of the facets that describe the data. Again, you can maximize the view of the facets, and here is another way to select the data the way you want without necessarily knowing anything about ESO data before. But the content is presented to you whether you know what was there a priori or not. This is, I think, the beauty of this facet concept. And again, you select the data, and once you're happy, then you download, as I showed you before. So there was imaging. Spectroscopy works very much the same way, because the funding principle of how we try to build an interface, well, to build the archive itself, in fact, through the standard that was mentioned many, many times earlier today. So how we build the archive itself and how we build then the access to the archive is that there should be no a priori difference on how the data was taken and the circumstances of how the data was taken but just whether it suits your scientific needs or not. So all of the data types, for example, they all end up in the same interface on purpose. And navigating through those will depend on what you're trying to do scientifically. But there's no a priori barrier in the archive guiding you or restraining you from going where you want to go. It's all there, all together for a purpose. And sometimes it is painful, as the people who have to navigate through the standard know, but this is the gold mine that we wanted to get out of that effort. So same interface as before, of course. It starts like this. This is the home, and then you enter another. Yes, it has started. You enter another target name, and as before, everything changes according to this constraint that you've put in. Again, footprints are shown on the sky. And here we refine the cone search a little bit. We use a different cone aperture, and now we go to spectra. Again, it means because all of the images tend to have a larger area are gone from our search, and we can focus in on what we were interested in. So spectra, you can see spectra, of course, are point-like sources rendered here as red squares. And again, you have your tabular view, and say that we want now high resolution spectra, because this is the kind of science we want to do. And so this is what we enter, and there's two ways of doing that. Clicking on the bar of a histogram that breaks down the possible values, or just entering the numbers in a text field, basically, in a number field. Then we do also want to have high signal to noise, because we're interested, say, in stellar absorption lines, whatever it is that we're interested in. So we've selected now a bunch of data, and for each of them we have previews. Just pop up immediately as you move your mouse over the table. And also there's ways, and this is now to go into details of a specific data set that you found particularly interesting in that in the coarser view that you had until now. So you click on a magnifying lens, I think it's the symbol. And so now you are zooming in on one specific data set. So you started for 4 million assets of all sorts of data, and now you are on the one that you might be interested in. You can zoom. This is the calcium triplet region. I'm sure you recognize it, and you inspect whatever aspect that it is that you're interested in, and you make sure that this is the data that has a promise, has a science promise towards reaching your science goal. Cubes, in sort of a progression of data complexity, so images are as simple as it gets. Spectra is already more complicated. Now let's talk about cubes. And the purpose of all of this is to show you that all of the data again look the same until they need to look different because they are different at the end, and you want to capture this variety. But at a higher level, they will look the same, and again, you zoom in until you find what you want. So let's do the same exercise that we did before for images and spectra. Let's do it for cubes, which again, arguably is a different beast in terms of data. And again, you start from an object. And by the way, there's no particular reason why you should be starting from a specific spot on the sky. You could also say, show me all of the spectra that have this signal to noise, this resolution, and this, because that is your science. You don't necessarily need to start from a positional search. This was just for convenience to show here. Now again, there's all sorts of data, because at the end of 25 years of observing the southern sky, you tend to have a lot of data in any given position of the sky. So wherever you go, there is a lot. And now we're down selecting by images to have a feeling for what's there. And you can see here that you can then show the image itself, the preview of the image itself on the sky, to put in context with the rest of what's there at that position in that spatial position. And this you can do with all sorts of previews. They can be shown directly there on the sky. Then again, we've selected now cubes as type of image of data. And we're selecting now spectral range because we don't want everything. We have something specific in mind to do. So we go through selecting for spectral range. Again, we can see the previews pop up. You can see these thumbnails pop up directly in real time. Oh, there was a nice gravitational arc there that I've just seen popping up in front of my eyes. There it is. I noticed it. And now I want to see what it really looks like. So what it really looks like, it's a dedicated page as the one that we've seen before for the spectra, but this time it's for cubes. And cubes are defined by being three-dimensional, so that you can see there on the left-hand side a 2D rendering of a 3D cube, which is just a white light image. It's just collapsed on the spectral dimension, but then clicking on that thing shows you the spectrum at that specific position you have clicked. Okay? It takes a couple of seconds because cube data are big, but it renders in almost real time, and then you can play around, say, with the positioning again and the aperture you want to be displayed in 1D, so the spectral projection, and again you explore your data and until you're happy, and then you download and you start your work. So what I showed you earlier was based, all of the, again, I'm already mentioned that they are based on positional searches, but of a cone. This is good and well, but it's of course not everything you may want to do. You may want to have contours on the sky that are not described by a single cone. And there are many reasons why you might want to do that. If you, like me, like, I say, the Magellanic clouds tend to have a very regular shape on the sky, so a cone will never do. Or if you have, say, a large area of the sky that you're interested in, for example, say contours from a gravitational wave event, which certainly cannot be described by any stretch of imagination with a cone. And you see a few examples there, and none of them is really cone-like, but some of them are really, really not cone-like at all. So we've built in this capability where you can search by any shape, any arbitrary shape on the sky for as long as you can, specify it as a simple string of dots. You can do that by clicking on the interface directly, or you can upload a file. This is what I'm going to show you now. And so we go to, so we go to our disk, we identify where we have our description of the polygon on the sky, and then we upload it to the interface, drag and drop, and it shows up. So this is all the intersection of the ESO assets with some gravitational wave event. I believe that this is the one with a neutron star with an optical counterpart. And you have that, and you can see all of the ESO assets. Again, spectra, cubes, ALMA, you name it, all of it is there. What we're working on now in this specific aspect is to see if we can link directly from the source of the gravitational wave contours, so that what you will be specifying, say, is the name of the event you're interested in, and all of the rest then happens in the background, unknown to you and automatically. And then again, you've selected some assets, and you can do all the previewing and everything else that I showed you earlier in order to make sure that this is really the data you want. Another thing is that searching the archive one object at a time is fascinating, but it might take a while if you have a lot of targets, which again is not that uncommon. Let's put it like this. In modern astronomy, it's probably actually the thing you want to do. So in order to do that, what you can do is upload a list of targets. So earlier it was a list of positions in the sky to make a contour. This is a list of targets, and it can be by position, it can be by name to be resolved, and you can specify also some other quantities, like for example the radius around the object and other things. I don't know if the demo started. It has now, perhaps. Yes. So sorry, I spoke a bit too fast because the demo hadn't started yet. So here we want to have images around a list of positions on the sky, and you do that by specifying your constraints. We want J-band, we want, I don't remember what it is we want anymore, but we'll find out soon enough. So the principle is that you specify again the physical properties that your results have to have. So we want an exposure time, and we enter all of these constraints. And we say to the archive, look, we want to upload a list of targets. We do that. The other thing that we may want to do is that these individual targets that I'm interested in are part of very large images. And you've heard all of how big the field of view of Vista, of Omega Cam and VIRCAM, to speak properly, were. And you may not be interested in all of the billions of pixels that each of the images are interested in, because you want the target you're interested in. So there is also a cutout service where you specify around a position of the sky that you don't want the whole thing that comes, the whole package that comes with a specific observation being part, say, of a VIRCAM frame. You just want that position on the sky. And if you make this very clear to the ESO archive by saying, I want a cutout, this is what the ESO archive will return you, just a cutout around the positions that you're interested in. Again, it's an attempt to reduce the complexity for the user from the flood of data that is available to what people are really interested in. So you specified all of this, the search was done, and then at the download time you specify, look, I want a cutout, and this is another way of downloading the data, of expecting the results. And here, this down them all is a plugin to the browser. This is not something we've done because we didn't think we could do it better than the people who actually can do that, but it has the functionality of, resuming the download and other things, monitoring the download. So this is really nothing too astronomical, really. It's just another way of interacting with the archive, with a download, let's say, more specifically, in terms of making it user-friendly. If something goes wrong with a download, you can resume it. You can see graphically how it's progressing and all of the rest. Then you wait what you need to wait, and you have your data on disk. Fine, we've explored a few of the data types in the ESO archive. Last thing I believe this is, or second last, we'll find out, is that catalogs. Of course, catalogs in the sense of the crown jewel to all of the hierarchy that goes from raw data to products to be used directly for science. There are huge effort to be made, as I suppose that all of the PIs and contributors to the phase 3 can testify, but they're really, really, really a powerful science resource. And again, the way you let me start this time. Again, you go to the ESO homepage, you go to the catalog tab, and you're presented with all of the catalogs that are present in the ESO archive. Thanks again to the efforts of our community who engage into generating these catalogs. We're just serving them. And here you see that at this point, the search is really, really pencil beam sharp to the characteristics of the catalog. You want galaxies with a certain profile. If that is in the catalog, this is what you're going to do. Not just what you're going to get, not just the basic magnitude and position searches, but really the physical characteristics at this time of the sources, the astrophysical sources. Okay, so this is incredibly rich as science resource. And again, once again, you select what you want. You can also link back to the data that generated the catalog, because okay, you see something, say, this looks fishy perhaps. Let me go back to the data and see what it really looks like. And more often than not, you will find that it really looks like what the catalog says, but it's incredibly important to be able to go back and check and make up your own mind as to the quality of the data that then you're going to publish in your name. Of course, citing where it comes from, hopefully. And again, you put in your requests and you download whatever you need to download. So that is the web interface to the ESO archive. In this last couple of minutes, I want to go back to a discussion that we had earlier, where we started earlier on. There's only so much complexity that you can build in a web interface. The goal of that is to do it, to render it useful, to render it easy to understand. So you click here and there and you figure out how it works. But there's only, again, so much complexity you can build into that. if you want to access the full complexity of data, you need to have a different approach. And this different approach is the virtual observatory. And this is done in two ways. The virtual observatory gives you access to specialized tools that speak to the data who speak VO, and then it allows you programmatic access to whatever it is that you want to on the searches. As an example of a VO tool, a very popular, and I always forget to click twice. This is Aladdin, the desktop version of Aladdin, which talks to all sorts of VO resources. In this particular case, we'll have it talk to the ESO VO resources, of course. So this, you are browsing the ESO archive through an external tool via the power of the virtual observatory. And the good thing here is that you have, at that point, at your disposal, all of the data and all of the powers that these tools have developed. I don't remember who mentioned that Topcat is not their cup of tea, for example, but for, yeah, for you, I guess. For a lot of people, it is, and it allows you to do a lot of complicated things on catalogs, and that you can do on the ESO catalogs through the Topcat interface. And again, without basically any barrier to doing that. If you know Topcat, you have all of the ESO catalogs in a familiar environment to you at your fingertip. This is an example, it's not on Topcat, but the principle applies just the same. So this is a query. By the way, you don't have to query to enter that complicated EDQL query. This is done for you in this particular case, because you're using still an interface, that's Aladdin, but you have that power. The results, you can see it in the background, there we go, appear on the backdrop of Aladdin. And at that point, you have all of the things that Aladdin allows you to do. You do another query on another telescope, another observatory, another data center, and it's all there, and you can do cross correlation, you can overplot, you can do whatever it is that your science asks you to. Now in a second, okay, one of the things you can do in Aladdin is to do plots. Again, everything is loaded there, and you have the capability of doing 2D plots and select your data based on that. Okay, so trust me, at the end you will get a 2D plot, but in the interest of time, let me move on to the last case. Now this is, if you really want to do something very complicated, and complicated doesn't mean bad, of course, this needs to be allowed. This is something you want to do as a scientist finding the data to do your science. You can have full access, of course, to the programmatic VO layer, let's call it like that, where through standard protocols, and also there are, of course, Python APIs that make things much simpler, but still very powerful. You can access the data and the metadata and treat them to do them whatever it is that you want out of them. So this is then, yeah, the Python script. There's a page that's also accessible from archive.eso.org, which again, if there is one thing to remember out of everything that I said, is archive.eso.org. Everything else comes, natural, but that's the thing. Archive.eso.org is the thing I would ask you to remember out of all of this. There is a page from archive.eso.org that links to documentation, to a community forum where exchanges on how to use and what to do with the ESO data take place. And also there are examples of scripting of different sorts directly with ADQL and or with Python. And this is the end